Take a look at this. Every machine perfectly synchronized, every belt fully saturated. No bottlenecks, no stuttering, just pure, uninterrupted flow. Today, we're going to build an end-to-end value chain for automation science. What does that mean? It means the factory is completely self-contained. It relies on nothing else. We feed it the absolute raw, unrefined materials: iron ore, copper ore, and coal. And it handles every single step of the transformation internally, outputting 900 red science packs every single minute. Hello engineers, I'm Max, and today we are going to explore the architecture of a very simple, complete factory. Let's break it down. To understand the system, we first must look at its structure, the bones of the architecture. I've designed this simple blueprint for the early to mid-game. We are using steel furnaces, assembly machine Mark IIs, and basic yellow and red belts. Alright, first let's go and take a look at our interface, our inputs and outputs. I believe in centralized routing. What does that mean? It means you should never have to drag belts to 5 different corners of a blueprint. Here we have our ingress. 1 yellow belt of copper ore, 1 yellow belt of coal, and 1 red belt of iron ore. Beside them is our egress, the single yellow belt where our finished red science will exit. It's clean, localized, and ready to plug into your main bus or train network. Okay, let's build this together. This is our first transformation tier. To achieve our goal of 15 red science per second, we require exactly 15 copper plates per second. This sub-factory or smelting array uses 24 steel furnaces to perfectly convert our yellow belt of copper ore into a yellow belt of finished plates. Next comes our heavy iron processing. Since red science requires iron gears, our iron demands are exactly double our copper demands. Here, 48 steel furnaces swallow 30 iron ore per second, which is exactly why we used a red belt for the input, and output 30 iron plates per second. Those plates are then immediately consumed by an array of 10 assembly machines, instantly transforming them into 15 iron gears per second. Our raw materials are now fully processed intermediate items. Now it's time to bring everything together. Let's build the core of the monolith. To produce 900 science per minute, we need exactly 100 Mark II assembly machines. If we built this in a straight line, it would become an architectural nightmare to fit into a base. So we fold it. We run the logistics up the center and fold the factory back on itself. You'll notice I'm using belt weaving here, braiding red and yellow underground belts together. From a purely practical standpoint, a standard lane balancer might do the job. But architecture isn't just about math, it's also about art. I chose this woven design because it's aesthetically pleasing. It's a signature on the canvas. Okay, structure is good and beautiful, but a factory is meant to breathe. Let's go and open the floodgates and watch the system transition from a static design into dynamic operation. The raw ore floods the system. The smelters roar to life. Watch the flow of materials. It's a cascading wave of transformation. Ore becomes plate, plate becomes gear, and eventually they all find their way into the final factory. Look at this particular design choice. Copper plates and iron gears each require a full yellow belt. But to save some space and keep the architecture elegant, I sideloaded them onto a single red belt, 1 item per lane. This is an intentional choice to use higher tier logistics here to keep the factory spine narrow and clean. Now, as the intermediate goods reach the final assembly line, you will notice something important. The red science doesn't output at capacity. But why? This is known as a manifold design. Because we feed a single line of machines, the first machines are greedy and consume the resources, starving the machines at the end of the line. The factory is now in a transient state. We have to be a bit patient. As the first machines fill their internal buffers, the resources bypass them, flowing deeper and deeper into the array. Let's wait for the saturation and let the system reach its steady state. Meanwhile, let's look at this part. As the output flows back down to our egress point, it passes through these lane balancers. Because of our folded design, the output can sometimes be slightly asymmetrical. These balancers act as our final quality control, making sure that the single yellow belt leaving our factory is perfectly compressed and flawlessly balanced. And there it is, a complete encapsulated value chain from raw ore to automated knowledge. If you would like to drop this exact monolith into your own world, the blueprint is available for my Patreons. I'm Max, and I'll see you in the next one.